Okay. All right. So I will share the slides. Okay. All right. Okay. No, not this one. Okay. There we go. Always ask me. Okay. All right. Can you hear? Can you see the slides? Yes, you can, right? Okay, good. Okay. All right. Yep. Let's start it. All right. Thank you. All right. So yeah, we're gonna start to talk about the frequency response, and I'm pretty sure that you already seen the lecture notes for the control one, right? So I already made it available on this course website. You know what? I would strongly suggest you guys, okay, download the lecture notes and so for your own study, okay. Do not leave it on the blackboard, okay, because the blackboard has some time to be open, right? Okay, so download it. Okay, it's free. Come on, right? Okay, okay, all right. So yeah, today we're gonna talk about the frequency response. And actually, I started this topic in control one at the end of the control one, right? If you can remember that. And so we've just talked about it a little bit, and then control one was completed, right? So now we're gonna go for the frequency response in detail, okay? Now, basically, the frequency response, it's all about two plots, okay? Here you can see the Bode plot, okay, and the polar plot, okay. The polar plot sometimes uh, it's another way to draw the frequency response, okay. So Bode plot is one way, the polar plot is the other way, okay. And um, from the polar plot, we're gonna derive the so-called Nyquist plot, okay. So the Nyquist plot actually is this polar plot, not something new, okay. So as long as you know this two plot, the Nyquist plot is going to be a special case of the polar plot, and so you're going to get it, okay. And also there is a relation between the polar plot and the Bode plot, okay. So once you understand these two plots and also their relation, then frequency response pretty much is there, okay. So let's see how it go, okay. And so, oh, wait a minute, why it's stuck in here? You know what, guys, I really don't like this virtual classroom, okay. So let me see. Fatty, oh my god, you guys need to talk to Team is also not good, okay. The best one is Zoom, so you guys need to talk to the university and ask them to change it, okay. Microsoft Team is also hard to use, but anyway, okay. How am I gonna change the page? And why is like that? Wait a minute, it's only one page here. That's impossible. Okay. So If I change the page, can you guys see that? Okay, good. Okay, okay. Yeah, it does not allow me to change the page in the virtual classroom. Okay, you know, I have to manipulate it in in the browser. Okay, now the frequency response. If you remember, we talk about the testing signal for the physical system. Is that right? Okay. Can someone tell me? Can you remember what kind of a testing signal we mentioned? Okay. Can someone give me some you know, answers? Okay. Testing signal. Yes. Unit ramp. Unit step. Right. Okay. Yeah. Okay. So, you know, if you remember, when we talk about the transient performance, we actually use the unit step response, right, to define the performance index in the unit step response specifically, right? So unit step is a very popular, you know, testing signal, because under the unit step excitation, and the system can respond, can exhibit its dynamic mode with a lot of information. So that is why people like to use the testing, the unit step as the testing signal. But for the unit ramp and unit acceleration, you know what? Because they were closely related to the, you know, the unit step, right? If you take the integral of the unit step signal, that is a unit ramp signal. So exactly, you can analyze the response to a unit ramp signal from the analysis of the unit step response. Okay, so they are closely related. Okay, you're not doing something really new there if you use different kind of a testing signal of unit step, unit ramp, or unit acceleration. Okay, now I also mentioned that there's another kind of a testing signal, and that is what we call the frequency signal. Okay, the frequency signal, it's a different signal, testing signal from the unit step and the unit ramp. Okay, in the sense that you cannot simply derive the response to a frequency signal from the unit step response or unit ramp, you know, response. Okay, so they are different. They are totally different. Okay, they're totally different. When you the difference, the one obvious difference is that if you analyze the unit step response, and both the response and the input, I mean the testing signal, they're all on the time domain, right? If you recall, we use the unit step response, you know, that you know, oscillation, you know, curve, right? If you remember that signal, that curve is on the time domain. So basically, the analysis of the unit step response, it's all in the time domain. Okay, it did not change the domain. Okay, but the frequency signal is different. Okay, frequency signal, you see, if you look at this picture, this is the setup for the frequency, to the experiment for you to get the frequency response. Okay, say you have a physical system here, and you have the physical system here, and you have a signal generator. I'm pretty sure you are very familiar with that signal generator, right? Because we have this device in the lab. And yeah, so you use that signal generator to generate a signal that at the certain oscillating at a certain frequency. Okay, and so you can see the lower part here shows this. It's a sine wave. Okay, it's a sine wave. Okay, so if you use this signal to excite the system, and of course the system will respond to that, and you can actually use a signal analyzer to get the, you know, the response to that specific, you know, frequency signal. Okay, And so this is the experiment setup to get the frequency response. But the difference, like what I said, the difference is that when you conduct a frequency response analysis, you actually can conduct the analysis on the frequency domain, not on time domain. This is the biggest difference, okay? And it is this frequency domain analysis give us a lot of information about the system, behavior, okay? So when we conduct this frequency response analysis, we have to, in your brain, you have to be able to switch the domain. We're no longer, conduct analysis on time domain. Instead, we're gonna conduct an analysis on the frequency domain. So let's see how we can do it, okay? And you might wondering that so what exactly the frequency response brings to us? Well, actually, to answer this question, there is a very simple answer. The simple answer is what? Is that solely because a physical system, if you use different kind of frequency signals to excite it, and the capability of the physical system to respond to that a specific frequency signal is different. In other words, if you change if you vary the input, the testing frequency signals frequency, yeah, in a spectrum, in a range of frequency, okay? Actually, if you have the experience to use the signal generator, you probably already know that you do have the capability to vary the frequency. Actually, it is in continuous format, okay? When I say continuous format, I mean that the variation of the frequency can be made very, very, very small, okay? So you can make the frequency change almost continuous, okay? So when the frequency span in an interval, in a range, we call that a range is spectrum, okay? We call that a range is a spectrum. So if you do this kind of experiment, then you're gonna find out that a physical system's capability to respond a signal in that spectrum is different. Okay, so just because of that, capability is different. Okay, it's straightforward. If the capability is the same, if you say you vary the frequency, of the signal, and the response does not change, then why should we conduct this kind of a frequency response analysis? It does not make any sense, okay? Because it's all same, right? Okay, just because the capability is different, so we found out that, okay, and this is very interesting. If we know the capability of the physical system with respect to response to a specific frequency, and then I will be able to manage to how to manipulate the system, okay? So this is exactly the frequency response analysis gives to us. So let's see how we're gonna go, okay? Now, so then, yeah, what exactly is the frequency response? Okay, we talk about the definition, okay? So this definition might come from math, but it does carry a physical, interpretation, okay? Now, what is the frequency response? Frequency response is the steady state response of a dynamic system, G of S. Well, G of S here is a transfer function model, okay? It's a transfer function model, okay? It's a dynamic system, G of S, the steady state response to a sinusoid testing input signal. Now, the key word here is steady state, okay? Steady state, yeah, you probably know what does the steady state mean, because in the control one, we did talk about the steady state, right? Steady state means that all the transient processes settle, okay? Eventually, the system is going to converge, I mean, the signal is going to converge to a certain value, okay? So this is steady state is that it's a clean response, okay? The transient, during the transient, the system behavior may behave, quite differently, okay? But eventually, the system works in the steady state, okay? Operate at a steady state. So the transient, you can simply think that, oh, the transient is, it's just a process, okay? It's just a process. The system has to go through that process, right? So it does not mean too much. What we exactly means is the steady state, okay? So this frequency response is defined to be the steady state. But you see, here, this is the sinusoidal testing input signal. So you might want to say, why the frequency response, a steady state response is so important? Because if you recall, when you use unit step signal to test the system, so what is the steady state response of that system with respect to a unit step? You knew that, right? It's actually eventually converges to a value, constant value, okay? A constant value. And actually, that value can be obtained from the Laplace transformation's final value theorem, right? We talk about that, right? As long as the system is stable, okay? It will always converges to a constant value, okay? So if it is the response is converges to the constant value, like what I said, it doesn't matter you use different kind of step signal, okay? You have the unit, you have the non-unit. If you just change the magnitude of the step signal, it will just give you different, constant. The behavior stays same. It's just the value is different. I mean, the set of the value is different. So that make the steady state response of a unit steps, testing signal boring. It does not give me too much information. But this is different from the frequency response. Here we define, okay? Because your testing signal right now, it's a sinusoidal signal. It's a oscillating, signal in certain frequency. So you're going to find out that the steady state response of a dynamic system to this kind of a testing input signal will no longer be a constant. Will no longer be a constant, okay? Instead, it will oscillate too at the same frequency of the testing input signal. But the magnitude will be different. The magnitude will be different. And also the phase with respect to the testing input signal, sinusoidal signal, will be different, okay? You can set, intentionally set the testing input sinusoidal signal's initial phase to be 0. Then you're going to find out that for different kind of a dynamic system, the steady state response, to this testing signal will carry a different kind of, different value of the initial phase, okay? So the phase is different, magnitude is different. Not only that, even if you do not change the initial phase and do not change the magnitude of the sinusoidal input signal, it only changes the frequency, the response, steady state response magnitude, and the initial phase. You see, here, what I'm in this figure is here, okay? The magnitude MO and the initial phase of the response signal, they're all vary along with the frequency, okay? They all vary along with the frequency. So that make the situation interesting. That make the analysis worthwhile, okay? Because there is a difference. And this difference is caused by the frequency. So because of that, we can actually, find out the relation between the MO, phi O, which is the output signals of the system's magnitude and initial phase. So we can actually find out the relation between MO and the M of W and the phi O and the phi W. Okay? Why? Because you see, this M of W and the phi of W, they can actually obtain from the transfer function G of S, right? So if you can remember, you see, the G of S, here I'm make this, very clear. You see, this is the dynamic system transfer function model, and you can get actually G of J omega by making S. In other words, you make the real part of the S. This is the complex, variable, right? If you remember, we talk about the imaginary part happens to be the frequency. Okay, so if you make the S, to be the J omega, which is taking the imaginary part of the of S, and then you will get a G of J omega, and this G of J omega is a complex function of omega of the frequency. Okay, and then you can actually because it's a complex function, then you can actually get its magnitude and its phase. Okay, so you can write actually G of J omega in this kind of expression. Okay, M of omega multiply e to the j phi of omega. Okay, and also you can write them in the real and the imaginary part, right? Okay, this is all math manipulation. And if you recall, we talked about the preliminary, the complex number and the complex variable, complex functions at the beginning of the the control one. So you can always manipulate this math derivation. Okay. What is the question here? Why do you choose R of t equal to mi sine? Okay. See, that's a sinusoidal signal, right? Abdallah? That's a sinusoidal signal. Okay. So if because we try to see the frequency response, right? That's exactly what I've just explained. Because I want to use a oscillating signal to test the system and see the capability of the system to respond to the different kind of frequency signal. Okay, see here, I want to vary the frequency omega and see how the system is going to respond to that. That's the reason. Okay, that's the reason. Okay, yeah. So now you can see that. So you can see this is the see the system. Okay, Brian, that's a good question. Okay, if you use a triangular wave, okay, the Fourier transformation, or if you use a triangle wave in a frequency, you can actually conduct a Fourier series. You know that a triangular wave actually can be decomposed into a Fourier series expression. Do you get my point? You see, the Fourier series analysis for a triangular wave, will be able to turn the triangular wave into the superposition, right, in terms of the sines and the cosines, right? So you see, you use triangular wave, actually by nature, it is equivalent to you to use a series of a sine and cosine wave with different kind of frequency. So eventually, you can reduce the response to the triangular, testing signal into the response to the frequency oscillation signal. So that is why we only need to know how the system responds to the frequency signal. Okay, we can actually use that response to derive whatever periodic signals that you want, square wave, triangular, whatever. As long as it's oscillation, it's a periodic signal, I can always derive that. You get my point? And on the other hand, here the analysis conducted here it's more than the triangular, use a specific triangular, wave signal. Why? Because if you see this mass here, we allow omega to vary continuously in the spectrum. Okay, continuously. Okay, I don't miss any frequency. But if you use a certain, periodic triangular wave, even if you conduct the Fourier series, decomposition, and the frequency in the Fourier series, if you recall the mass, okay, the frequency in the Fourier series are always discrete, not continuous. In other words, it can only include certain discrete values of the frequency in the spectrum, not the continuous spectrum. So if you compare the two way to do the analysis, here our analysis here allow the frequency to vary continuously in the spectrum, definitely is more rigorous. Okay, definitely is more rigorous, right? I did not miss anything. Okay, I catch every frequency. Okay, but if you use a periodic, triangular wave, you can only catch the response to a certain, frequency value, not all of the, frequency value. You see what I mean? Okay, so that is why to conduct the frequency response here, it's good enough. It's good enough. I do not need to use other kind of periodic testing signal. Okay, okay. So now actually here it is very important for you to know how this mass is gonna be operated. Okay, I'm gonna give you example here. Okay, so but I have to switch the board. Okay, unfortunately I cannot share the two. I cannot share the, oh yeah, I do have an example here. Okay, yeah, I do have an example here. You see the example here, you see, let's say if your system is modeled by a 1 over s plus 2, okay, the model is a 1 over s plus 2 transfer function model. Okay, so then you the g of j omega, okay, it's gonna be expressed, can be obtained by 1 over j omega plus 2. Like what I said, you set s equal to j omega. Okay, now for this one, you can write this 1 over j omega plus 2. This is a complex function and of the frequency omega, right? So like what I said here, I can express this complex function in two formats. One is the magnitude plus the phase, or the real part of this complex function and the imaginary part of this complex function. So in this example, you can see I can figure out what is going to be the magnitude. Yeah, magnitude is the double bar of the g of j omega, which can be derived very easily through this 1 over square root of omega squared plus 4, right? So this is you know how to manipulate that. And not only that, I can also get its phase. Okay, the phase phi of j omega. This is the g of s, the system's phase. Okay, the system's phase. Okay, so you get this phi of phi of omega is equal to the minus tangent inverse omega over 2. Okay, see, you can get the magnitude and the phase, and then you can write down the it is in this format, right? M of omega, phi of omega, e to the j of phi omega. Now, if you want to express it in the real imaginary part, yeah, you can do it. You see, here we can figure out the real part of this j of j omega. It's a function too. Okay, it's a function of a frequency too, right? See, this is going to be simply equal to the 2 over omega squared plus 4. You have to rationalize the denominator to do that. Okay, you see, we had this kind of a manipulation practice in the control 1, right? So you rationalize the denominator, and then you can factorize this complex function into two parts. One is it's a real part, which is also a function of frequency, and the imaginary part, which is another function of a frequency, and the imaginary part is going to be equal to here. So you can also express this g of j omega in the real and the imaginary part. Okay, now, yeah, a numerical example here, can give you this. So you see, this is the sinusoidal signal. Okay, for the sinusoidal signal, and you can see it's frequency is 2. Okay, and under this testing signal, then you can see the system. Okay, g of s is gonna give you a magnitude that is equal to 1/2 square root of 2. And the phase provided by the system at this specific frequency 2 rads per second is going to be equal to the -45 degree. They can be computed from this 2 formula, right? Okay. So you can see at the omega equal to 2, the system actually provides a negative phase. Okay, the system actually provides a negative phase. Okay, so this is the manipulation of the g of s and the g of j omega, and write it down in two expression. Okay, so you should be very familiar with this two expression. Okay, and also you should be able to convert between these two expression, in a minute. Okay, the formula is given here. Okay, because later on, you're gonna find out that we always try to, use this one of this expression, and the other one sometime, and the other expression at the other time, and also we are also interested in the relation between these two expression. Okay, between these two expression. So you should be once again, you should be very familiar with this two expression. Okay, now see, if we see this numerical example, then we already found out that, oh yeah, the phase of the system could be negative for a certain kind of frequency. Not surprisingly, you can find another system that with respect to the same frequency signal, and you can find out that the phase actually could be the positive. Okay, could be positive. Okay, could be negative, could be positive. So because in terms of this phase value, okay, the magnitude you might not be able to see the difference, right? Because it's all positive. Okay, but the phase is different. The phase provided by the system could be positive, could be negative. So it does make sense for us to use this phase to classify the system, okay, in terms of the frequency response, okay, in terms of frequency response, okay. For example, if the system provides a positive phase, then we call it a phase lead. If the system is provide a negative phase, then we call it a phase lag, okay. And yes, so what is your question? Oh, that's a good question. You know what? Normally, if the system provides a negative phase, it should be the whole spectrum. Okay. Okay. That's a very good question, Jason. Okay. And actually, the fact is that you cannot have as long as the system is described by the transfer function, then you're going to find out that if a system is a phase lead system, the phase is always positive. Okay, it doesn't matter which frequency you're gonna use. If the system is a phase lag, it will always negative. The phase, it will always negative. Okay, it doesn't matter which frequency you're gonna use. Okay, you see, Jason, this is raised a very good question here, is that if you do have a system that exhibits a positive phase and for a certain kind of frequency, and the negative phase for other frequency, then we cannot use this phase lead, phase lag to classify the system. You understand that? Because it causes confusion. So the reason I can use this to classify the system is just because it's a unique feature. Okay, it will not cause any confusion. You got my point, right? Okay, so this is fortunately we have this hard effect. Okay, if a system is a phase lead, its phase it will be always positive. It doesn't matter which frequency you're going to use. Okay, vice versa for the phase lag. Okay, so in other words, for any dynamic system described by the transfer function, it will be either phase lead or phase lag. No confusion. Okay, one of them. Okay, no confusion, right? So this is a good classification. Okay, yeah. Okay. Any other question? Any other question? No? Okay, good. Okay, so now, yeah, so what let me see. I have, okay, so we back to this expression. So why because you see just now you might want to ask this question. You see, in the definition, we define the frequency response actually is the steady state response of the dynamic system, G of S, to a sinusoidal testing input signal. In other words, the frequency response is actually defined on the MO omega and the phi O omega, right? But it seems like here you talk about the system, the G of S is the M of omega and the phi omega a lot. Why is it like that? Okay, well, you see, like what I said, is the reason that we can do this is just because there is a unique relation between M of omega and the MO of omega and the phi of omega and the phi O sub O of omega. Okay, because of that unique relation, we actually do not need to bother to look at the signal. We only need to look at the system. That's good enough. Okay, because in other words, M of omega and the phi of omega, they uniquely determine the frequency response as defined here of a system. You got my point? If it is not, if we do not have that kind of a relation, then we cannot do that. Okay, we have to check the signal itself. Okay, but it's just fortunate we do have this kind of a relation, so we do not need to worry about the signal. We only need to look at the system, the M of omega and the phi omega. So what is that relation? Yeah, it's here. You see, the relation is that C of t, the signal here, the C of t, you see, C of t is a signal here, right? The output signal, the response signal. Okay, if you assume the input signal is a sinusoid and with a magnitude that is mi and the frequency omega, and then you're going to find out that the steady state response of this dynamic system G of S, which is the signal here C of t, that is going to be equal to the M of omega multiply mi and the sine omega t plus phi of omega. Did you see the relation here? Did you see the relation here? So you're going to find out, oh no, now I understand. The magnitude of the response signal is going to be simply equal to the product of M of omega multiply mi. Okay? So in other words, the magnitude is always N of omega times the mi, the input signal's magnitude. Amplifier, you can understand this way, right? It works like an amplifier. Amplified by how many times? M of omega times. And this M of omega, this times, will change when the frequency changes. Okay? But the MI, you actually can fix that. Okay? You do not vary the MI, because varying the MI does not give you too much. Okay? So it's always M of omega times. Okay? So in other words, if we can catch how many times this system is going to exaggerate, the input signal's magnitude, that's good enough. You got my point, right? M of omega actually is the system's capability to exaggerate the input signal. Okay. Now, I ask you to understand this as an amplifying way. Well, it does not mean that the system is always amplifying the input signal's magnitude. Okay. Apparently, if m of omega is larger than 1, and then the output signal, it will be increased. Magnitude will be increased. Will be bigger than mi. If m of omega is less than 1, then what? Then your output signal, response signal's magnitude will be less than the input signal's magnitude. Is that right? This is a very obvious factor that we can derive from this expression, right? Okay. So in other words, the m of omega represents the capability of the system to exaggerate or reduce the input signal's magnitude's capability. Is that right? Do you agree with me? Okay, right? So if you want to know if the system is good for a input signal at a certain frequency, it will exaggerate that signal or reduce the magnitude for that frequency signal. You only need to check m of omega. Is that right? Good enough. You only need to check m of omega. Okay. So if you capture the features of the m of omega, you pretty much capture the capability of the systems to respond to a certain frequency signal. Okay, so this is the magnitude. Now let's look at the phase. So you can see that omega t plus phi omega. See, this is phi o omega because we set the input signal here is the initial phase is what is 0, right? So in this case, your phi o is going to be simply equal to the phi of omega. The relation is straightforward, right? So you want to check phi o omega? Okay, you just need to check the phi of omega. That's good enough. And again, this phi of omega is the information that we can derive from the G of S, from the system transfer function model. So in other words, you don't need to look at the output signal. You just need to look at the system's models itself. You can drag the capability of this system to respond to a certain frequency response, input signal, right? Testing signal, right? So if you check the m of omega and the phi of omega, good enough. Now you might want to ask yourself, what about the initial phase of the input testing signal is not 0? Yeah, it's possible. Then I can tell you that. Can someone tell me that in this case, what is going to be the initial phase of the response signal? Give me a quick answer. Someone, please. Equal to what? You know what? I actually allow you guys to write on the board. Okay, so you can write on the slides. Okay, if you want, you can write your answer on the slides. Okay, so what is if the initial phase of the input testing signal is not 0? So what is going to be the initial phase of the response signal phi o? Tell me that. Okay, someone? Quickly, I want a quick response. Come on, guys. Someone jump up. Hello? Phi I plus phi omega. Right, yes, Abraham. Yeah. So yeah, that is okay. So when you look at that expression, the phi I is what you set. So you already know. So this phi o is going to be equal to phi I and the phi of omega. Again, as long as you know the phi of omega, then you know the phi o of omega, right? Okay. So you can see that it does not matter the initial phase of the input testing signal is 0 or not 0. As long as I know the phi of omega, I know everything. I know everything. Okay, I know everything about the phase. Right. So because of that, we can actually reduce the frequency response of a dynamic system from its signal case, here, from its signal case to what? To m of omega and the phi of omega. Okay, to the m of omega and the phi of omega. Okay, okay. See, this is a very important conversion. Okay, we changed the picture. Okay, we converted the picture. Okay, we converted the picture from examination of the signal into the examination of the system transfer function model, and specifically, it is m of omega and the phi of omega. Okay, so from now on, then we're gonna, anytime when we mention the frequency response of the system, we always refer to m of omega and the phi of omega. You agree with me? Okay, you got my point. Okay, we no longer mention the signal, the output signal. Okay, we always refer to the m of omega and the phi of omega. Okay, and besides, like what I said, we actually can use the phi of omega to classify a system. Okay, we can classify them into a phase lead or phase lag system. Okay, that is good, very good. Okay, so the information is rich here. Okay. So yeah, then it is clear that we now we now reach an agreement that okay, in order to understand the frequency response of a dynamic system, I need to examine m of omega and the phi of omega. Okay, now the next question is like, how are you going to do that? How? Well, you see, actually from this example, let me go back to this example again. Okay, to get some clue. Okay, say, you see, for this g of s equal to 1 of s plus 2. And I have the m of omega equal to 1 over square root of omega squared plus 4. And the phi omega is equal to minus tangent inverse of omega over 2. And it is very clear they both are function of omega, right? So in other words, if you vary, remember we said that the frequency response is that we allow the frequency varies continuously in a spectrum. Okay, so here the spectrum is what? Is that omega from 0 to what? Infinity, right? That's what I want. The full spectrum. I want to know how the system is responds to any frequency signal in that spectrum. So in order to examine that, I need to allow omega vary from 0 to infinity. Yeah, then you see this function already gives a explicit expression, and to allow me to evaluate the capability. And for this specific system, did you find out that when you make the omega starting from the omega equal to 0, and then your magnitude actually is equal to the 1 over 2, it's 0.5. Actually, apparently, we can conclude that at the frequency equal to 0, the magnitude actually is the biggest, is the highest, right? You see, as the omega increase from 0 to infinity, you see, when the omega reaches infinity, what is m of omega's value? What is that? It's 0, right? You see, apparently, if omega is, goes to the infinity, and the magnitude m of omega is what? Is 0. So what does that mean? M of omega, equal to 0. You see, if we go back to look at here, m of omega equal to 0 when omega is equal to the infinity. What is the value magnitude of a response signal? 0. Okay, 0, 2. In other words, if you test the system, let a signal, well, assume you can really generate a frequency that is equal to the infinity, okay? Practically, it cannot be, right? Practically, it cannot be. Actually, it's not necessary to let the frequency to be the infinity. As long as the frequency is high enough, this value m of omega will be very small. You're going to see the magnitude of the response signal to be very small. In other words, the system will block that frequency signal. Okay, the system will block that frequency signal. Okay, so what's your question? Well, that's a good question. Okay, large enough. It depends on how you can. Well, actually, later on we're going to introduce the definition. It's a bandwidth, right? Bandwidth, right? Bandwidth means that acceptable signal level. Okay. Bandwidth means that acceptable signal magnitude level. Okay. Well, actually, you don't need to make the omega accepted. Well, accepted by the bottom line is that if the response signal's magnitude too small, it's useless. But how small is small depends on the bandwidth. We're gonna clearly define the acceptable level later. Okay, by using the technical term bandwidth to do that. Okay, so you're gonna see that. Okay, so we can define what is small. It's called a small. Okay, here you just need to understand that the system could block certain kind of frequency signal because the magnitude m of omega could be very small. Okay, if the magnitude is small, I don't care about the phase. Okay, because the magnitude is so small, it's useless. The signal is already useless to me. Okay, so in this sense, we're going to say that the system has the capability to block the signals, input signals. You see, m of omega small means that it is very hard for an input signal at that frequency to pass through your system. Understand the other way is the filter, right? You see, high pass filter, low pass filter is apparently for this example here, one of S plus 2. If you want to use a high pass filter, low pass filter to describe the system, now tell me that the system is a high pass filter, is a low pass filter. You guys have the concept of the high pass filter and low pass filter, right? You guys have the signal processing course. Is that right? Okay, so you tell me what kind of filter this system is going to be. One of S plus 2. High pass or low pass? Low pass. Yes, apparently it's a low pass, right? Apparently it's a low pass. Because for any high frequency signal, it is very hard for a signal to pass through. So now you see why we are concerned about the frequency response. Okay? Because we really want to know what kind of a signal can pass through the system without any obstacle. Okay? Other system, which signal is going to be hard to pass through the system. If we know the system, this kind of a capability, it will be very good for me to manipulate the system. Okay? So you're going to see that. Okay? Now, on the other hand, you can see the same thing for the phi of omega. So when omega changes, the phi of omega is going to change, apparently, right? Say, okay, so the frequency, you see, when the frequency is equal to 0, the phi of omega is actually equal to 0. So when the frequency increase, because this is positive, that the tangent functions, the property is that when the omega is large, is positive, this phase is going to be always negative. Okay, this phase is going to be always negative, right? Okay, it cannot, as long as you change the sign of omega. But what does the negative frequency means? Physically, you cannot do that, right? So practically, you can only do that mathematically. So that is why we can use this phase to classify the system. Okay. This system will only be phase lead when you have the negative frequency, testing signal. But as long as you can Abdallah, that's exactly what I mean here, right? How will you be able to generate negative frequency? Only in the mass, right? Only in the mass sense. Physically, you won't be able to have a signal that carries a negative frequency. And I've never seen that, right? So that is why this phi of omega is always negative. Okay, and apparently you can see that when the omega, you see, when the omega goes to infinity, what is this phase? Can you answer that? What is this phase? What is this phase value? When the omega goes to infinity, approaches to infinity, what is this phase? Come on, quickly. 0? Yeah. Negative. Ziad, be careful. Not 90 degrees, minus 90 degree, okay? Yeah. Minus 90 degree, okay? Minus 90 degree, okay? That's very important, Ziad. Okay, positive 90 degree and the negative 90 degree, they're totally different, okay? One is a phase lead, the other one is a phase lag, okay? Okay, but in this special example case, you know, the phase actually, you can see that the phi of omega, you can see that for the whole spectrum, from 0 to infinity, the phase actually varies from 0 to the negative 90 degree, okay? Negative 90 degree. Okay, so yeah, so here this is the special numerical example. Just say to the omega equal to 2, I've got this you know, m of 2 is equal to this value, and the phi of 2 is actually equal to minus 45 degree. Okay, so since my interest is to evaluate m of omega and the phi omega, then it makes a lot of sense for me to find a way to plot it. And that is what we introduced here is the Bode plot, okay? The Bode plot actually is trying to, Bode plot consists of two plots, okay? One is the magnitude plot to describe m of omega. M of omega's change along the frequency range, okay? You see, the horizontal axis here is actually the frequency. And the vertical part, yeah. You see here, we are doing some manipulation, mass manipulation, okay? We're not using the absolute value m of omega, okay? But we do not want to distort the picture, okay? You know, we use the 20 log. I will explain why people like to use the 20 log, okay? And, you know, but you see, when you use the log m of omega, did you realize that, you know, the log value and the value itself, the number itself, you see, the log number, the number m of omega itself and its log value, they carry the same trend. Okay? So in this sense, the logarithm does not change, does not distort the picture of the trend. Okay? When I say to keep the same trend, I mean that if m increase, log value is going to be increased. If m decrease, log value is decrease. You know, remember here, what we want to know is exactly how big this value is going to be along with the variation of the frequency, right? So as long as I know the m of omega increase along with the frequency, or decrease along with the trend, as long as I know the trend, the value, it really doesn't matter for me to use m of omega or log m of omega. Okay? You got my point, right? Because they keep the same trend. And you want to know, they represent the capability, they did not distort the system's capability to respond to a frequency signal's picture, right? Okay? Okay, the trend is the same. But why we use log, you know, m of omega? Yeah, you're going to find out that, you know, the log carries one advantage is that if, let's say, if you have a product of two transfer function. Let's say you have a m1 of omega multiply m2 of omega, and then you take the log value. What is that? Then the logarithm operation turns the product into a addition. Okay, a logarithm operation turns the product of a two value into an addition of the log value, right? Okay, so here you just need to know this is going to be the advantage that we're going to take. But later on, we're going to find out that for a control system, we're always facing what? Facing the cascade connection of the system. If you remember, the cascade system's transfer function model is equal to what? It's equal to the product of the individual block, transfer function, right? Okay, so if you want to evaluate a cascade system's frequency response, and under the logarithm operation, you have a lot of advantage because you only need to do the addition, not the product. Okay, so later on, when we talk about the system analysis, you're going to see the advantage. So this is one reason that we use the log. Okay, now why 20? I don't know. You can find out. I mean, maybe you can find out. Let me know. Okay. And I have tried to figure out why is 20, but unfortunately I could not find any clue. Okay, but anyway, so because 20 log is the well accepted set, okay, setup for in the community, in engineering and academic community, right? So we have to accept that. Okay, yeah. Question? Power reason? No, I don't think so. Okay, yeah. Okay, so, then you can see that the Bode plot is very clear. Okay, for the magnitude plot, the horizontal, axis is frequency. Okay, I have something to talk about the omega frequency. Okay, you can see that the omega frequency could be used omega itself, or could be used log omega. Okay, it could be also used log value. Well, the good things to use log value is that you can see this figure shows very clearly. If you use omega itself, and it will not be even. Do you see that? The scale will not be even. This is 0.1 ras per second. This is 1 ras per second. And this is 0.2, 0.3, 0.4. So if you use a logarithm, then you can actually have a even scale. You see, because the logarithm incremental by every 10 times. This, by the way, this log is the base 10 logarithm. Okay, base 10, not the natural base. Okay, natural base is e, right? So here is base 10. So base 10, the scale is even every 10 times, right? So you can see here. This represents 0.1. 0.1 is log omega equal to 0.1. I mean, the real value is 0.1 rats, but on the logarithm, it's gonna be the -1. So this is the 1. This is a 10. This is 100. So you can see that if you use the logarithm, you can compress the range of the frequency in a more effective way. Okay. You can express the frequency response in a short interval. Okay, you can describe quite a large spectrum in a short interval. Okay, so this is the advantage of the only advantage of using log omega. Okay, once again, you do not change the trend. Okay, so you use omega or log omega, it's okay. The trend is going to be the same, right? So that is why we normally, when we draw the Bode plot for the m of omega, we always like to use logarithm for both omega frequency and the vertical frequency. You got my point? You got my point? Okay. See, you can see that the correspondence here is this. The real value is 0.1, right? 0.1 rest per second. Under the logarithm, this value is going to be -1. And this one represents the value omega equal to 1 rest per second. In logarithm, this value is what? 0. So -1, 0 here. This one is what? Is 1. Okay? In logarithm is 1. This one is what? In logarithm is what? Is 2. You can see that? See, in the logarithm, the scale is even. Okay? You have a uniform, scale. -1, 0, 1, 2. Okay? So it's good looking. Good looking. Okay? So it's compressed the frequency in this short range. Okay? Compress the frequency in this short range. Okay? Okay? And also the vertical value is 20 log m. Okay? So this is the Bode plot's magnitude plot. Okay? This is Bode's magnitude plot. And specifically for this special example, if you draw, it's basically this, right? It's basically this. Okay? Okay? Okay, this plot, you can always use MATLAB to generate it, okay? You can use MATLAB to generate it, okay? Actually, when you conduct a real analysis and control design later on, you're going to find out that you do need this plot. So you do need accurate plot. So you can always use MATLAB to draw it. But there's another way to do approximation, okay? To do approximation, we'll talk about that. It's not accurate plot, but sometimes it's useful, okay? So do not worry about, all I want to say is that do not worry about the drawing, okay? I'm not quite sure. You might want to, give more details of that analysis. I don't know. I mean, actually, 20 or 10, I don't know. Okay, I don't know. I mean, here, where the 10 log 10 come from? I don't know what you mean. Okay, but anyway, I'm not quite sure. Okay, so this is why is 20. Again, I'm not quite sure. Okay. Okay. So now the phase plot comparing with the magnitude plot is much simpler. Okay, because there's not much games that we play here. Okay, the phase we just plot is a real value. Okay, real value phi of omega, and the frequency response, frequency axis is the same like the magnitude, plot. Okay, so you can use logarithm, log scale, okay, to express that. Okay, see for this picture, it's very clear. This is the Bode plot for this special system g of s equal to 1 over s plus 2. Okay, so consists, like what I said, consists of 2 plots. Okay, consists of 2 plots. Okay. Yeah, follow this line. And do I have time? Yeah, I don't have much more time, so probably I'm gonna go for the. So I would suggest that you guys go through the lecture, the remaining part of this slides, okay, to look at it. See, the remaining part of this slides is just basically tell you the examples, for each specific special systems, okay, the Bode plot, okay. For example, if you have a simple gain system, okay, which means that the g of s is just equal to the k, and of course the 20 log m omega is only equal to the 20 log k. You see that? You see, it's simply determined by the value of k. Okay, simply determined by the value of k. And what is going to be the phase? The phase is 0 because you only have a gain k. It's a real number, right? A real number. Okay, so the phi of omega is 0 everywhere for all the frequencies, right? Okay, it doesn't matter which frequency, the phi omega, in other words, the phase shifting provided by the system is always 0 degree. Okay, always 0 degree. Okay, okay. Now, second example is integration. Okay, integration is that g of s is equal to 1 over s to the n, power of n, right? This is an integrator. You know that. When you have a power of n, we mean that you actually have n integrator in this system. Okay, so for this kind of a system, you're gonna find out that g of j omega is equal to this, and m of omega is actually equal to 1 over omega to the n. Okay, right? You see, this is integrator. Integrator is like what? It's also a low pass filter. Okay, also a low pass filter, and depends on how many integrator you're gonna have. When the omega increase, the decrease of the m of omega is significant. Okay, when you have n is larger than 1, well, n can always larger than or equal to 1 because n is an integer. Okay, positive integer, right? Okay, yeah. So the magnitude decreasing is quite significant. Okay, it's a power of n times. Okay, decrease. And what about the phase? You can see that depends on the number of n, number of integrator. If you have one integrator, it will shift, it will provide a phase lag of minus 90 degree. 2 integrator, minus 180 degree. 3 integrator, minus 270 degree, right? Okay, so this integrator is always phase lag system, okay? And also it is a very much low pass filter, okay? Very much low pass filter. It has a very narrow band, spectrum that to allow the system pass, to allow the signal pass through, okay? As long as the omega increase a little bit, you can see because of the n, the power of n, so the decreasing is significant, okay? The decreasing is significant, okay? So we can actually also draw the Bode plot for this integration, right? So it's here. You see, it's here. This one corresponds to the n equal to 1 case, okay? N equal to 1 case, okay? And you see, this is the minus 90 degree, and the n equal to 1. Then you're gonna see the drop of the magnitude. You see, this is the m of omega drop along with the time, okay? Along with the frequency increasing, right? And the slope of this line actually is minus 20 dB per decade, okay? This can be, proved it's a line, okay? It's a linear, okay? And differentiation, yeah, you can see, not surprisingly, you're gonna see the magnitude actually is increasing, right? It's increasing, you see? Not only increase, it increases to quite fast, depends on the power of n, right? Okay, for the n equal to 1 case, and the slope is 20 dB per decade, okay? Decade means 10 times frequency, okay? Increase by 10 times the frequency, okay? Every 10 times increase of the frequency, the magnitude is gonna go up by 20 dB. Here is decreased by 20 dB. Every 10 times the frequency, right? And for the differentiation, and apparently the phase provided by the system, by the differentiation is positive. So this is the phase lead system. And the phase lead provided is depends on the n. For n equal to 1, it's 90 degree. Otherwise, it's going to be 180, 270, blah, blah, blah. All right? Okay? So, and it is also interesting to notice that this magnitude and this magnitude, you know what? They are actually symmetric with respect to the frequency axis. They are symmetric, okay? You see, they are symmetric. Even the phase is symmetric, right? Because this is a 90 degree. If you draw them in the same chart and same chart, then this minus 90 degrees is going to be here, okay? It's going to be here, right? So they are always symmetric with respect to the frequency axis, okay? So if you draw, if you draw the same the magnitude in the same chart, you're going to find out that this one, if you draw that, it's going to be here, okay? It's going to go in this way, okay? So I would encourage you to look at to examine this simple examples yourself after the class. Okay, and so yeah, that's pretty much about today's lecture. Do you have any questions? I have 2 minutes and I can take some questions. Okay. Okay, Andrew, thank you. Uh, uh, Anybody else? All right, Wally. All right. Okay, very good. What are the examples for leading and lagging system? Well, the lead and the lag only make sense when we do the control design. Okay, so Abraham, you might at this moment you just need to remember the technical terms of this lead, how this lead and lag are defined mathematically. Okay, and the physical interpretation, we're gonna talk about that later when we introduce the stability description in the frequency response. Okay, so you're gonna find out that actually the phase lag actually is harmful to the stability. Okay, the phase lead is beneficial to the stability. Okay, so because of that, you can add a controller in the sense of the controller should provide more phase lead or more phase lag. Do you see what I mean? Okay, so this concept will be used for the control design later. Okay, so at this moment, you just need to remember, okay, what kind of a system is phase lead? What kind of system is phase lag? And it is solely determined by its phi of omega. Okay, so once you have the transfer function model, in other words, once you have the transfer function model of a system, the system is phase lead or phase lag is already determined, right? Okay, all you need to do is to check its phi of omega. Okay, phi of omega, and that one should be easily done. Okay. Any other question? Any other question? All right. Okay. So if you don't have any other question, yeah, that's all for today.